This coin goes around one identical coin once, but it turns over twice. Watch the marked dot. It starts at the contact point, reaches the outside after half a lap, returns to the contact point at the top, reaches the outside again, and only then comes home. 2 complete turns. That looks wrong. If I cut the coins into 2 straight strips, each circumference long, rolling one along the other takes exactly 1 turn. So why does bending the stationary strip into a circle apparently manufacture an extra rotation? Before we explain it, make a prediction. If the moving coin starts on the right, where will its marked dot point after a quarter trip around the fixed coin? 1 turn per circuit would put it at the top. The actual coin puts it back on the right, exactly where it began pointing. It has already made half a turn, and that tells us what not to blame. The coin isn't slipping, the animation isn't counting the trip around as a rotation, and the marked dot isn't playing some coordinate system trick. Relative to the room, the coin really turns through 720 degrees. I used to picture the moving coin tracing the circumference of the fixed one, which makes 1 turn feel unavoidable. But that picture quietly tracks the wrong path. Not slightly wrong either. It misses the distance that controls the roll by a factor of 2. So, which point is actually traveling around which circle? The point that matters first is the moving coin center, and it doesn't travel along the fixed coin's rim. It can't. That center must always stay 1 moving radius beyond the fixed rim. Call each radius r. The centers are therefore separated by r plus r, so the moving center traces a circle of radius 2r. There it is, the missing distance. One orbit has length 2 pi times 2r, which is 4 pi r. The moving coin's own circumference is 2 pi r. If rolling converts 1 coin's circumference of travel into 1 rotation, then 4 pi r divided by 2 pi r is 2. The arithmetic is almost offensively short once the correct circle is visible. But hold on. We should be suspicious here, because rolling on a curved surface isn't obviously the same as rolling along a flat road. The center travels 4 pi r, yes, but does center distance alone always determine rotation? Imagine an enormous fixed coin. Locally its edge looks flat, and the rule seems fine. Shrink that fixed coin down, though, and the direction of the surface itself swings continuously underneath the roller. That turning direction is exactly where most explanations become slippery. So the path length calculation gives the right answer, but it hasn't yet exposed the mechanism. To do that, we need to stop watching the whole coin and watch the one point that is forbidden to move, the contact point. Forbidden only for an instant, which is the interesting part. At every instant, the 2 coins touch at a point that is stationary relative to the fixed coin. No slipping means the material point on the rolling coin that meets it must also have 0 velocity at that instant. Now split the moving coin's motion into 2 pieces. Its center is sweeping around the fixed center. At the rightmost position, that center moves upward. If the coin were merely carried upward without rotating, every point on it would move upward, including the contact point. Bad. The surfaces would slide past each other. Rotation has to cancel that motion exactly at contact. A counterclockwise spinning coin makes its leftmost point move downward relative to its center, so upward translation plus downward rotational motion gives 0. Match their speeds. The center travels at speed 2 or times the orbital angular speed. The rim moves at speed r times the coin's spin rate. To cancel, r times spin rate must equal 2r times orbital rate. The r disappears, leaving spin rate equals twice orbital rate. 1 orbit, 2 spins. And notice how local this is. We didn't count dots after the fact. The no-slip condition demands the factor of 2 at every single moment. Move to the top of the fixed coin and the directions have rotated, but the cancellation is identical. Center motion left, rim motion right at contact. The contact point keeps changing. Each tiny patch arrives, stops for 1 instant, then leaves. So now the 2 turns are mechanically forced. But the original straight strip argument is still sitting there, looking betrayed. Where precisely did its missing turn go? The straight strip didn't lose a turn. Bending the track added one. Picture carrying the moving coin around the fixed one while refusing to let it roll relative to the local tangent. Keep the same face of the moving coin aimed outward at all times. After 1 circuit, that face has gone right, up, left, down, and right again. Relative to the room, the coin has rotated once, even though relative to the track it hasn't rolled at all. That's the hidden turn. The track's tangent makes 1 full rotation as you go around any simple circle. Actual rolling adds another rotation relative to that turning tangent, because the fixed coin circumference and the moving coin circumference are equal. 1 from following the changing surface direction, plus 1 from rolling along the surface, equals 2 relative to the room. On a straight strip, the tangent never turns, so that first contribution is 0. Only the rolling turn remains. This is the assumption that broke. We treated 1 circumference of edge passed as the whole rotation, while silently measuring orientation against a frame attached to the surface. Fine on a straight road, where that frame never changes. Not fine when the road curls all the way around. You can see both contributions if we run two ghost coins together. One is carried around, always facing outward, 1 turn. The other rolls an additional turn relative to it, 2 turns total. Nice, but equal coins are almost too tidy. If the rolling coin changes size, does the hidden turn stay 1, or was that another coincidence? The hidden turn stays exactly 1. The other contribution changes with the size ratio. Let the fixed coin have radius r and the rolling coin radius r. The moving center now travels on a circle of radius r plus r, so one orbit covers 2 pi times r plus r. Divide by the rolling coin circumference, 2 pi r, and the number of turns is r plus r over r. That's r over r plus 1. The plus 1 is the part people miss. It comes from the rolling coin's own radius being included in the center's orbital path, or, in the turning frame picture, from the tangent itself rotating once. Take a rolling coin half the radius of the fixed one. R over r is 2, then add 1, 3 turns. Watch the mark. 1, 2, 3. Make the rolling coin 1/3 the radius and it turns 4 times. Make it twice as large as the fixed coin and the answer is 1.5 turns. That last one looks especially odd because the moving coin dwarfs the thing it's orbiting, but the contact rule doesn't care about dignity. The center still traces radius r plus r. There is a useful limit here. As the fixed radius grows enormous, r over r dominates, and the extra one becomes a tiny fraction of the total. The track looks flatter and flatter, so forgetting the curved frame turn hurts less. But now, let's reverse the geometry. Put the rolling coin inside a circular track. The center path becomes r minus r. Does the mysterious one get added again, or does curvature finally take it back? Inside the track, curvature takes the turn back. The rolling coin center traces a circle of radius r minus r, so the same no-slip calculation gives r minus r over r turns in magnitude, r over r minus 1. The tangent frame still rotates once during the trip, but now it turns in the opposite sense from the coin's rolling contribution. Outside, those rotations reinforce each other. Inside, they oppose. Here is a sharp test. Let the large circle have twice the radius of the small coin. The formula says 2 minus 1 equals 1 turn. As the small coin rolls once around the inside, its center traces a circle whose radius equals its own radius. Mark a point on the small rim. The point doesn't trace some complicated loop. It moves back and forth along a straight diameter. That is wonderfully severe. We change the plus to a minus, and the looping path collapses into a line. If the small radius is 1/3 of the large one, the coin makes 2 turns, and the marked point draws a 3-cusp curve. These are hypocycloids, paths made by a point on a circle rolling inside another circle. Outside gives the related epicycloids. The original 2-coin puzzle is the simplest outside case, but the extra turn isn't a party trick attached to coins. It's a curvature correction, and it controls the geometry of every one of these trace paths. One caveat that matters: we're counting orientation relative to the room. Count turns relative to the rotating line between the centers, and you'll subtract that frame turn again. Same motion, different reference. So, can we identify the 2 turns on the original coin without any counters at all? Yes. Return to the 2 equal coins and ignore the counter. Just watch when the marked dot touches the stationary coin. It begins at the contact point on the right. After the moving center travels halfway around, the coins meet on the left side of the fixed coin, and the marked dot is at contact again. A material point on the rolling coin has returned to the contact position after only half an orbit. That is 1 full rotation. The second half repeats it. 2. Another way to see it is to mark 4 equally spaced points on the rolling rim. During one trip around, each point reaches the inward contact direction twice. 8 contact events, 4 marks, 2 cycles. None of this depends on the coins having teeth or on us pretending their circumferences are straight. It comes from one constraint: the contacting surfaces have no relative motion. For equal coins outside each other, the center travels around a circle twice the coin's radius, and the local tangent turns once along the way. Those are the same facts seen globally and locally. Path length says 4 pi r divided by 2 pi r. The rotating frame picture says 1 turn from following the circle plus 1 from rolling. The velocity picture says the rim must move twice as fast angularly as the center line. 3 routes, same stubborn answer. Now the opening motion should look different. The second turn isn't appearing from nowhere. The first guess threw away the moving coin's radius, and with it, an entire circumference of travel. Roll the coin once more. The center makes 1 quiet loop. The mark goes around twice, exactly as it has to.